Now there's one final solenoid topic I'd like us to take a look at, a quick look at, before we move on to other topics. And this third example, so this is solenoid example number 3. This third example is going to help us understand a little bit more about conservation of energy. If you think about Faraday's law, the integral of E dot dl is no longer 0. That means that the electric field is no longer a conservative field. So you might begin to wonder, as we deal with these Faraday law circuit elements, whether energy is conserved or not. So let's see how we might try to get at that issue. Now, to get at that, this third example is going to be a very particularly simple form of circuit. So what I'm going to have is a resistance R, and I'm going to have this circuit, it's going to have some current that's flowing through this circuit already at time t equals 0. And then I'm going to have my inductor, L, and then that's going to be it. I'm just going to have an RL circuit. I'm going to dispense with the battery. And when I do this, the current I is going to be some function of time t. And my initial condition is going to be that the current at time t equals 0 had some initial value, which I'm going to call, say, I naught. Now, you might ask, what happens? How is this system going to behave? Now, how we got to this situation in the first place, that might be a little bit of a longer story. Clearly, what must have happened is there must have been some EMF in the circuit at the beginning, some battery, right, that powered up this inductor and got the current flowing through it. And then I threw some kind of a switch which took that EMF out of the circuit. Now, when we think about the behavior of the current as a function of time t, and try to make a sketch of what we're going to expect, what we know is that, again, the current had a value I naught at the very beginning, right? Somehow we had gotten this thing powered up. But there can't be any discontinuity in the behavior of the current. We know eventually it's going to slow down and stop because of this resistance, right? But initially it has to have the same value. It has to be continuous. So it's going to start wanting to decrease, but it has to come in here continuously. And if we begin to think about it, you might begin to realize that, oh, wait, this is probably going to decay then down towards 0 with some particular type of a decay behavior. So let's see now if behavior. And the interesting thing is that as it does that, there's going to be current flowing, and there's going to be power dissipated in this resistor. So that tells us that somehow there is actually energy stored in this inductor somehow in some form, and that energy ultimately gets drained out through the resistor through this type of process. And we have a chance then, by adding up all the power in the resistor, figuring out how much energy is actually stored in that inductor. And that's really kind of our goal. Now, to carry out this analysis, once again, we're going to use one of our Kirchhoff's loops. This time I'm going to, just for variety, do it in the opposite direction, because you can do Kirchhoff's law in any direction. So this is going to be the effective K2 that I'm going to carry out. I'm going to start here. Now, notice we have a presumed direction of flow of the current. So once again, the upstream side, as the current is flowing down through here, is a plus. The downstream side is minus, and similarly for the resistance. And then if I start, say, at my point here labeled X, I know then what K2 is going to tell me will be, 0 equals, going around my loop here, I'm going from plus to minus along this, I'm going to go this way, right? So I'm going to go through my inductor. I'm going around this way. As I go through that inductor now, I'm going from the minus side to the plus side of the inductor. So plus or minus L times di dt is the effective voltage, but because I'm going from the minus to the plus side, that comes in as a plus sign. Similarly, as I come across the resistance, I'm going upstream through the resistance from minus to plus. So that's, again, plus or minus IR, but in this case, it's actually going to be plus. And then I can rearrange my equation here, and what I find is by moving, say, di dt to the other side, of the L di dt to the other side of the equation, what I find here, if I rearrange things a little bit, is just that IR has this interesting value for this circuit of minus L times di dt. Now, the reason why I want to do this is I want to think about conservation of energy. So if energy is actually conserved, what that means then is that the power that's coming out of this circuit through that resistor, right? That's the rate of change of energy, right? That must equal the energy that changes that are happening to my inductor. That must equal, and again, in this course, it's always plus or minus until we figure out the right sign, the time derivative of the energy in the inductor. That has to be the case if we are able to account for energy changes in our inductor as being conserved, meaning that we can account for all the energy leaving the inductor as energy going out of the circuit into that resistance. Now, if to determine the sign, we would expect if power is coming out of the resistor, that must mean that we have a decreasing amount of energy stored in the inductor. And if that's decreasing energy stored, this time derivative should be negative. And for the signs to come out for a positive power coming out, we must choose this here minus sign. Now, what do we know about the power through the resistance? Well, that we know because we have a number of formulas that we've used over and over again for a resistor. We know the power out of a resistor is I squared times R. And we can rearrange this, of course. Frequently, we write this as I times IR. In other words, I times the voltage across the resistor. IV is another one of our standard power formulas. I write it in this form, though, because I'm trying to track my signs very carefully, and I know what IR is. I times R for this circuit is always minus L times di dt. So I'm going to get minus I, but IR being minus L times di dt, I can substitute that in here, and I'll get minus I L times di dt. And this is nice because when I put it all together, I can now equate the energy in the inductor to the changes in the current through the inductor. When I equate this term, I have minus du, the energy in the inductor dt, has to match, this is nice, minus, so those minus signs will cancel, the inductance L times current I times di dt. And of course, let's cancel out our minus signs. Well, that's a very nice result, because if that is true, I think I can integrate this to figure out the energy that's stored in the inductor. Right? If we think about it, we want to integrate both sides here with respect to time t. Right? So this would mean that the energy stored in the inductor should equal capital U, that's why I put these little horns on there. I want something whose derivative gives me back I. So that sounds like it should be a function like I squared. So I would guess this would be something like, I need my constant L, of course, probably I squared. And that's nice, because when I take the time derivative of both sides, I get dul dt on this side, and I'll get L times 2I times di dt, which is exactly what I have here, except I'm missing a factor of 1/2. So there will be a factor of 1/2. Finally, of course, when we integrate both sides, you might worry that there's some constant of integration plus c, but I think it's very reasonable for us to say that, well, if we have, in fact, zero current flowing through our inductor, if it's just sitting there with no current, there should be no energy stored in it, right? I can't suck more energy by having that inductor continue to pump current out through anything if the current starts out as 0. So if the current is 0, I know the energy stored is 0, so that tells me that this constant here actually must be 0. we now have a very nice formula for energy in an inductor, very similar to energy in a capacitor, right? It just involves now current and inductance instead of charge and capacitance.